So I decided to do this talk for a number of reasons, but the main reason was that this new version of the Commodore 64 that came out when I was 15 years old originally, they came out with a new one, and it was the first time where the little sense of nostalgia really hit right. I bought a Commodore off eBay one time, the Commodore 64, and it's like, I can't do anything with this. This one has the exact right balance of being true to the original hardware, but also having a lot of convenience. And it made me decide, okay, I would really like to tell people more about the time that I grew up in programming, which was sort of unique because we worked very closely with the hardware. Working with hardware has a very different feel to it than a lot of software development these days. And I think it really changed who I was as a developer by starting with working at a very low level with the hardware. So I wanted to give people both a little history of the personal computer, because that was fun for me to investigate because I didn't know all of it, and also to show you a little bit of programming, old school programming on a Commodore 64. So that's where this came from, and hopefully you'll enjoy it and get a little bit out of it, and maybe get a sense of nostalgia as well. So let's start with a little history of the personal computer. A lot of it started, it was made possible by the single-chip microprocessor, and that was made possible by a guy named Federico Faggin, who was an Italian immigrant, and while he's in Italy, working with Fairchild, he developed the MOS metal gate technology, and then when he came to the US, he developed the silicon gate technology, which is really the key to developing the microprocessor. So an interesting story happened. He went from Fairchild to Intel because Fairchild wasn't doing what he was interested in. And at the same time, a Japanese company called Visicom was looking for a new chipset for a calculator they were doing. They were assuming they'd do the same way they'd always done it with discrete chips. But the lead engineer on it basically came up with the idea that they could do it cheaper with less chips if they used RAM memory, which hadn't really been done in a calculator before. And they had this idea of coming up with a processor for it. And Federico Faggin developed that, and as part of it, he developed two key technologies that made it possible and cheaper to make a microprocessor. One was called buried leads, which basically allowed them to interconnect all of the transistors without a separate metal layer, so they could do it much more cheaply than they'd done before. And the other one was, let's see if I can find it here on my notes. Anyway, bootstrap loads. And that was a way of basically having capacitors that provided more voltage to the transistors. And that was normally thought, when they first developed the silicon gate technology, they thought that would be impossible to do on chip and it would require a lot of extra steps. And he did it without even an extra step in the processing. And so he was really key to developing the technologies that made the microprocessor possible. Now, along with him, one of the engineers from Visicom, Masatoshi Shima, he developed a lot of the logic for the first microprocessor, including bringing it down from 3 chips down to a single chip, which was the Intel 4004. This was a 4-bit processor, and it was what was used in the Visicom calculator, but it's what led to a very quick uptake in developing processors. So let's get to the next processors that came out. Very quickly, Motorola came out with the 6800 processor. This is an 8-bit processor, came out in 1974 for $175, which would be $1,000 today. That was followed by the Intel 8080 processor, they were charging $360 for that, which would be $2,000 today. And of course, Federico and Masatoshi developed that as well. But then Federico wasn't happy where Intel was going, so he moved to Zilog. And Zilog developed the Z80 processor, which was instruction compatible with the Intel 8080, but had a lot of new capabilities. It only required a single voltage, where the Intel 8080 required 3 different voltages coming in. It had a single phase clock, it had built-in DRAM refresh, and had some 16-bit registers, so it had a lot of extra power. And that's why the earliest version of the CPM operating system came out on the Z80, because it was a fairly powerful processor for the time. But as you can see, those were all fairly expensive processors. And an interesting thing happened while a guy named Chuck Peddle, who was working at Motorola on the 6800, he would go out to the marketing meetings to companies to market the 6800, And he saw that there was would be a real demand for a lower cost processor that was a little simpler. And Motorola didn't think that was the case. In fact, wrote him a letter to say stop working on that idea. So he decided to leave, and he ended up at MOS Technology, and ended up with 7 of the 18 members from the 6800 team coming with him and joining him on that. And the first thing they developed was a processor called the 6501. 6501 had a new instruction set, but it was pin compatible with the Motorola 6800. Well, Motorola wasn't happy with that, so they sued MOS Technology. And MOS Technology quickly came out with the 6502, which was not pin compatible with the Motorola, and so it wasn't going to be sued for it. But what was impressive about it is they announced it at a trade show at $25 a chip, and that's in quantities of 1. And so it was basically revolutionary at the time to have that low of a price, and made it possible for hobbyists to start developing computers. And we'll get into some of those important ones there. Some interesting things about this chip. It ran slower than the competitors like the Z80, but it had some interesting design to it. It first was the simple 2-stage pipeline. So for each cycle of the pipeline, it would first read from memory, and in the second cycle, it would do whatever processing that instruction was due, and would not touch memory during that second cycle. And that, number one, made it possible to have a lot of instructions that completed in only 2 cycles. And it also meant that other chips, like video and audio chips, could access RAM in that off cycle without having to have a bunch of bus contention logic. And so it ended up being faster. For comparison, the Zilog Z80 took 2 cycles just to fetch memory, and the minimum instruction time was 4 cycles. Now, to give you an idea of the complexity of a chip back then, the 6502 had about 4,500 transistors in it. The Z80 had about 8,500, so the 6502 was pretty simple. A little later on, the chip that became part of the first PC was the 8088 processor, had 29,000 transistors in it. And the 18 Pro that's in the new MacBook Neo, it has about 20 billion transistors in it. So we've changed pretty dramatically. Like the M2 Ultra has 134 billion transistors in it. So chips have changed quite a bit and grew very quickly. I want to talk about the 6502 and how it relates to the chips we use these days. One of the designers on the 6502 and the 6800 was a guy named Bill Mensch, and he later started a new company called Western Design Center, and they created a successor to the 6502 called the 65C02. And the interesting thing about that processor, it's still used today in embedded systems, including in medical systems like pacemakers and defibrillators. And I thought that was interesting. And a little later in 1985, some designers at Acorn Computers were looking to decide whether to buy a chipset to use in the next computer that they were going to do, or to design their own chip. So the designers went to 2 places. They first went to a modern 32-bit design house where a team of 12 engineers was working on revision H of their CISC processor and still had bugs in it. Then they went to the Western Design Center, and they saw high school students on Apple IIs laying out chips there, and decided at that point that they were going to stick with a RISC architecture. And they developed their first one was the Acorn RISC machine, which later became the Advanced RISC machine, which is the ARM processors that we know today that are in virtually everything we use. And interestingly enough, the original ARM processor instruction set was simulated on a BBC microcomputer, which was running a 6502 processor as well. So my feeling is that the 6502 has a real ancestry in what we look at today in the ARM chips. And I thought that was a little bit of fun. Now, we've looked at the microprocessor. Let's look at some computers. Now, the first one didn't use a microprocessor. It was the Kenback 1. It's considered the first personal computer, though. That's a big stretch of the word personal computer. Only 50 of them were built, 44 of them were sold. It was built on separate integrated circuits, not a microprocessor, a lot more like the mini computers of the time. And the only way to program it was through the switches on the front, and to see your output was on the lights that came out. So it was really only used for educational purposes because there was no other way to use it. There was no expansion to it whatsoever. But that quickly led to a very important computer of the time, and that's the MITS Altair 8800. This computer was built on the Intel 8080 processor. And when you first got it, it was a lot like that Kenback. You programmed it with switches and it had lights on the front, but it had an important difference. It had expansion slots, and those quickly got filled with extra RAM, with a serial interface, with video display interfaces and things like that. And people started working with them, and it was very popular. They sold 1,000 the first month, and over 10,000 of them in total. And some important software got its start on the Altair 8800, which I'll talk about in a few minutes. Another important first computer is the KIM 1. This was actually developed because Chuck Pendle needed a platform for people to learn, and to test and learn development on the 6502 processor. And so you can see it here. It was quite a bit more advanced than the Altair. It actually had a keypad where you get enter hex numbers and a digital display there, and it could also hook up to external displays. And it became really popular among programmers. A lot of books were written about 6502 assembly language, and it really inspired a lot of developers for creating computers. All right, before we get to the next group of personal computers that are a big leap beyond what you're seeing here, let's look at some of the influences of the time that helped bring them about. The first was the Homebrew Computer Club. This was started in Palo Alto, California. And at the first meeting in Gordon French's garage, they showed the Altair 8800. And at that meeting, Steve Wozniak saw that and was inspired to develop the Apple I by seeing that. And he showed the Apple I first at the Homebrew Computer Club as well. Some notable members, of course, were Wozniak and Jobs, Ron Nicholson, who was one of the Amiga computer designers, and a bunch of others. The club had a very open attitude towards sharing hardware ideas and software, which we'll get to in a minute, because that's another important influence of early computers was BASIC and Microsoft. And so first of all, the BASIC language, for those who don't know, was developed in 1964 at Dartmouth College. But William Henry Gates III, as he was known at the time, became familiar with it programming digital PDP mini computers while he was in high school. And he and Paul Allen started a company called Trafo Data. And it was a company where they were basically trying to analyze traffic data, but it wasn't doing very well. And when they saw the Altair 8800, they thought, well, we should do a BASIC interpreter for that. So they wrote the founder of MITS and said, hey, we have a BASIC interpreter for the Altair 8800. Would you be interested? And after a little back and forth, he said yes. Well, they hadn't actually written it yet. So they quickly wrote it. They actually wrote a 8080 emulator on a PDP mini computer and delivered the first version of BASIC for the MITS on a paper tape and loaded it up. Did print 2 plus 2, and it came out 4, and started selling it and tried to sell it for about $150 a pop. Now, one of the funny things about that was the Homebrew Computer Club was sharing that software around quite a bit, basically pirating it. And so Bill Gates wrote an open letter to hobbyists to basically say, can't keep doing this because we need to be able to make money, and it was sort of an interesting time. So even early back then, there was a lot of back and forth between sort of open software versus making a profit off of it. And basically you'll find that most of the computers of the time booted to a BASIC interpreter is the first thing they do, and you'll see that here with the Commodore 64. The other thing that was important back then were magazines. We didn't have the internet back then, and so these magazines were how you found out about basically everything to do with the new computers that were coming in. So Popular Electronics, highlighted, basically had the Altair 8800 on the cover and a number of other computers that it pushed. And then later came out Creative Computing, Byte Magazine, which is sort of the Bible of the industry, for computers and technology. And then one of my favorites was Compute and Compute's Gazette, which were dedicated to the 6502 processor and the different computers that you could work on for there. And it had a lot of programs that you could type in, and my first assembler was actually one I typed in. It was actually written in BASIC, but you typed it in and started it running. So it was a lot of fun. It was a very different time. But that was important to me, at least, for finding out about it. Now let's get to the next group of computers, which are very important. And that's the 1977 Trinity. There's the Commodore PET, the Apple II, of course, and the Radio Shack TRS-80, all came out in 1977. We'll go through each one in a little bit of detail. So the Commodore PET was interesting. As you can see, it's an all-in-one computer. It had the cassette player, had the monitor, a weird keyboard, but at least a keyboard. And it had a 4K version that came out at $495, 8K for $795. They sold about 200,000 of them. But its life ended a little earlier than some of the other computers from 1977, but that was primarily because Commodore released the Commodore 64. The TRS-80, this was a fun one as well. It was based on the Z80 processor. It had a full keyboard, floating point Microsoft Basic, a nice 64, well, I'll say a 64 column monitor, not a nice one. And it was well priced at $600 with monitor and cassette, so it was a complete system. The only sound it had was through the cassette player, so if you wanted any game with sound, you had to have the cassette player hooked up and it played through there. But in 1979, it had the largest software on the market and was the best selling until 1982. It was selling 5 times the amount of the Apple IIs. However, it was not so lovingly nicknamed the Trash 80, and it was for a lot of good reasons. The keyboard, even though it was a full keyboard, had a terrible bounce problem where every time you type a key, it would do 2 of them. It could be expanded, but the expansions were finicky and difficult, and it had a really poor quality monitor and was fairly unreliable. So it, over time, sort of faded, but it was popular for a while.
We have a question.
Uh-huh.
How did it play sound through a cassette? I don't understand that.
So almost all the computers at the time had interfaces to cassette, and they would actually store programs on cassette tapes, and they would do that by alternating tones, to do ones and zeros on there. And so it could send out a serial signal that would basically be, would play through the cassette player as though it were your auxiliary jack into the cassette player. Okay. So yeah.
That's crazy.
If you want, you can come in and sit down and watch it. Feel free if you want. Okay. So let's look at the Apple II next. The Apple II was obviously also based on the 6502. It was designed by Steve Wozniak, and the case was designed by Jerry Manick. Just so you'll know, Steve Jobs was not involved in the design of the Apple II. He came in after that. It had 4K of RAM originally, had a 24 by 40 column by 24 line display, had game paddle support. It had an integer basic initially that was written by Steve Wozniak, but it was quite a good basic. It had graphic commands, it could read off the paddles. One of the things he was most proud of is he wrote a breakout game to demonstrate at the Homebrew Computer Club, in BASIC on it, and so he was happy with that. But the integer BASIC sort of limited. Later they got AppleSoft BASIC, which was a Microsoft variant. The sound was fairly simplistic. It had a single toggle circuit to emit a click through the speaker, and you had to basically toggle it at the appropriate frequency to get sound out of it. And it required extremely difficult programming to get both sound and graphics at the same time. So those were sort of difficult parts of it. But it was extremely well made, and it had expansion slots, so it could be expanded very easily, and people started creating expansions for it that did quite a bit. It was also priced really high to begin with, so for the original 4K version it was about $1,300, which would be about $7,000 today, or for the 48K version it was about $2,700. And so it was lagging behind the others on sales. Now, an interesting thing happened that helped it along. A guy named Dan Bricklin was writing a piece of software, and the company he was working with had Commodore PETs, they had TRS-80s, and they had one Apple II sitting around. Well, the Apple II was the only one not being used, so the guy recommended that he use that and give it a try. And so Dan Bricklin wrote his software on there, and that was VisiCalc. And that became one of the things that really drove Apple's sales as a business computer, or at least being able to use it for personal business, and really helped it sell. And year over year, the Apple II just did better and better, and by the time it was ended production in 1993, they had sold 6 million of them. And Wozniak did some other, one of the things I want to talk about was the Disk 2, because it'll compare interestingly with Commodore's disk drive. The Disk 2 was the controller he did for the disk drive was really impressive. He reduced what was a common controller design by 10 less chips or 10 times less chips than were in the controllers then. They did all of the control of the writing in software so they could do their own format, so they could store more per disk. And it was very fast. It was, for the time, it was running 15,000 bits per second, storing and retrieving, which we'll compare in a minute to what was happening on the Commodore 64. Before we get to the Commodore 64, a few other computers that came out around the same time. There was the Atari 8-bit computers, the 400 and 800. They did very well, did about 2 million, but again, they couldn't compete with the Commodore 64 on price, so died off a little earlier. The Sinclair ZX81, this was the first one I bought myself, and typing on that membrane keyboard was a total nightmare. It had 1K of memory, so getting it to do anything in BASIC was pretty challenging. It had a 16K RAM expander you could put on it, but that would often come loose and then the whole computer would reboot and you'd lose everything. So that was lots of fun to work on. A really interesting computer of the time was the TI-99-4A. It was from Texas Instruments. It was the first 16-bit processor in a home computer, but it had some quirky mini computer design choices like registers and memory. But the bigger thing was that TI decided to strictly control development. And they did have a hobbyist community, they did provide technical info, an editor or assembler, and a prominent columnist at the time, Jerry Purnell, said, TI had rightly concluded that hobbyists and hackers were a tiny part of the market, and wrongly concluded that they were therefore unimportant. And that's why a lot of the other computers did so much better, is they had this hacker community that was developing software and moving them along. So the TI-99-4A did poorly to begin with, and they had a massive price war with the Commodore 64, which they certainly couldn't beat, and they dropped to as low as $99 in 1983 trying to get rid of them, and it did not do well. So that gets us to the computer we're talking about today, finally. That's the Commodore 64, and we'll get into a lot more detail about its architecture, but I'll at least briefly start here. It came with 64K of RAM and a variant of the 6502 processor called the 6510. It had a very advanced sound chip called the SID chip, a dedicated graphics chip called the VIC-2 chip, and Commodore could beat everybody on price because they had bought MOS technology in 1976, so they were producing all their own chips as well. So they released it in 1982. So what would I have been? I guess I would have been 17 at the time. And for $595, it quickly dropped down to about $299 is what I remembered at. And it is the highest selling single desktop computer of all time. It sold they estimate between 12.5 to 17 million units. And so it had a big part in a lot of people's development. Let's talk really quickly about some of the peripherals that the Commodore 64 came with. The first was the cassette player. And this was sort of interesting because it was better than the other cassette players. That most companies just use standard cassette players with an audio jack going in. Like I said, they'd alternate tones to do the bits. Well, this actually used square waves with parity bits to encode, so it was extremely reliable, though it was very slow. It was doing about, I thought it was slower than that. I guess it's 500 bits per second and could store about 100K on the 30-minute side of tape. So it was a different world back then. You'd stick in your tape, say load, and wait 10, 15 minutes for it to load up a very short piece of software. The next thing was the 1541 floppy disk drive. This turned out to be far more popular than Commodore had expected. 90% of Commodore 64 owners bought these, and they had only expected 30% to do it. But almost all of them got returned because they had some real quality problems with this device. And they finally got them worked out over time, but it had a really high failure rate. The main cause of the problem was the fact that it had no way to detect when the drive head was back at the original 0 position. So what they did, in an interesting idea, is that wherever it was, they would always step it back 40 tracks, which was the max number of tracks, so that they'd be sure it got to 0. But if it was at track 10, it would go 10 back and then bounce against the stop 30 more times. And so you'd hear this little ratcheting sound out of the drive all the time, and that also had a tendency to put it out of alignment fairly quickly. So it was not a great drive from the standpoint of reliability at first, but interestingly, it did have a 6502 CPU on it, a couple of input-output chips, and some people even found ways of loading up code to the 6502 to use it basically as a co-processor to do additional code running from the main processor. The last one is the 1702 monitor, and I only mention it because it was a really good monitor at the time. It was a split video monitor, which meant it had separate chroma and luma outputs, so it had a high quality to it, and yeah, it was just a nice monitor for a long time. All right, before we get into the details of, I should say the 1541 drive was extremely slow because it was trying to be compatible with an earlier drive they'd done, so it was only doing 512 bits per second, versus, like I talked about, the Apple II disk drive doing 15K bits per second, so it was a really slow disk drive. People found ways of making it faster later. There were cartridges that would allow fast loading, but it was a little weird. Before we get to the Commodore, let's talk about what just came right after that as things developed. We, of course, had the IBM PC, which was powered by the Intel 88 processor, and it sold extremely well, and obviously created the birth of all the clones that created the whole PC industry that we have today. Then there was the Apple Macintosh, which launched in 1984 at $2,500 with 128K and a floppy disk drive. It was initially considered underpowered and slow and didn't sell well at first, but when they brought out the 512K version and hard drives, and it found its market with desktop publishing, and it grew and grew and became what we know, the juggernaut we know today, with a few bumps along the road. And finally, one of my favorite computers was the Amiga from Commodore. Amiga was being developed as a separate computer, and then Commodore bought them. And it sold for $12.95 in 1985 with 256K of RAM. It had some really powerful chips for video and sound, and was one of the first, well, it was really probably the first personal computer with a multitasking OS. And it found its place in graphics and video, especially with a product called the Video Toaster, which was a card that allowed you to do live switching effects in there. And the first product that I developed in '93 was a product called Hollywood Effects, which was a 3D video effects software for the Amiga computer originally. And that led to selling that to a company called Pinnacle, which led to meeting my current business partner, which led to the business I'm in now. So things have a tendency to get you from one place to another, you know, little odd choices. And mine was happening. And the whole reason I went for a Commodore computer is because it was cheaper than an Apple. I would have loved to have had an Apple II at that time, but it was too expensive for me. So I went Commodore, and the rest was history. All right, so let's look at the Commodore 64 architecture. This is what the motherboard looked like at the time, and has a couple of I/O chips on the side, 3 ROM chips for the basic kernel and character ROMs. The main processor in the middle there, SID chip, VIC chip, and a few other things. We'll get into each of these in a little detail. So the 6510, it's fully 6502 compatible, but added I/O port pins directly on the CPU, and some controls for switching memory in and out, and also had some other address control things to make it better for working with the video and audio chips. The next one was the VIC-2 chip. This is the video interface chip, and it, as you can see, provided super high-res graphics with lots of colors, 16 whole colors in there, and had 320 by 200 pixel display, 40 by 25 characters. And a funny thing about the 16 colors, one of the engineers said at the time, "I'm afraid that not really as much effort went into the color selection as you'd think. Since we had a total control of the hue, saturation, and luminance, we picked colors that we liked. In order to save space on the chip, though, many of the colors were simply the opposite side of the color wheel from the ones we picked. That allowed us to reuse the existing resistor values rather than having to completely unique set for each color." So you can see at the time they were working with a very different set of limitations in designing chips for there. But it had some other fun things. It had 8 sprites that we'll see actually in action in a little demo that we'll do here, and could, at any point along the screen, could change modes so that people could do different graphic modes at different points along the display to do like a HUD, or, you know, as opposed to the game.
What is a sprite?
A sprite is and the other word is MOB, movable object. It is a little graphic that is separate from the normal graphics pipeline, and so the hardware would directly put it on screen and move it around separate from everything else that was going on. It was like think of it as an overlay, but it was hardware controlled, and so it could move quickly. It even had the ability to detect collisions between other sprites, so that you could use it primarily in game development, where you could use it for characters that are moving around the screen. But it was also fairly easy to program compared to, you know, because you could basically program the data for the sprite, which we'll see here in a minute, and then just basically tell it how to move around, and it would move around on screen. And for the time, that was pretty revolutionary to have that. The next chip was probably the most important chip in the Commodore 64, and that's the SID chip. It was really unique and advanced for its era. The designer, Bob Yanis, would later produce digital synthesizers at Ensoniq and did some other things as well. It was interesting. He originally what he said was that other sound hardware of the time was obviously not designed by people who knew anything about music. He really wanted to do something more. Originally, he wanted to have 32 different independent voices, but both time and money made that a little difficult. So they ended up with one that just has 3 voices in it. But for each voice, you can basically select the waveform type. You can select what's called ADSR, which is attack, decay, sustain, and release, which is the shape of the sound coming out and how it falls off, so that you can get different types of instruments out of it, I guess is the best way to put it. And then had mixers to allow you to do some other types of effects. Now, the Commodore 64 was used in something that was called the demo scene, where started with hackers who were cracking software, but they would always put a cool demo on there to show off how capable they were as engineers. And so that became a scene unto itself where people do these impressive graphic and audio demos. It was much bigger in Europe than here in the US. It's still big today. They still have these big meetups of people doing new demos on the Commodore 64 all the time. But almost any 8-bit game you play now with sound that sounds 8-bit was probably based on the concepts that came out of the SID chip. In fact, people still develop music and sound effects on it specifically for 8-bit games now. All right, so that brings us to the computer we're going to look at today, and this is a remake of the Commodore 64 called the Commodore 64 Ultimate. A bunch of the original engineers of the Commodore actually got together along with some other people and decided that they wanted to create something truly unique, and so what they did is built a Commodore 64 on a FPGA chip, an AMD FPGA chip, and it's a faithful creation of the original motherboard with a lot of extras in it. So they added HDMI, USB, Wi-Fi. Instead of just one SID chip, you can actually emulate 8 SID chips have been done in the FPGA, and they've even added slots for real SID chips in there for 2 of them. So that's how big the music part of it was, that people really want the original chip in there so that they get the true SID experience. It's compatible with all original Amiga hardware. You can put in cartridges, you can put in drives, you can do all the little extras that they had for it. And then they added some extra software to make it easy to control, to mount drives off of USB, to get on the internet and get things. They even did a modem emulation over Wi-Fi, so you can get on the old bulletin board systems on the internet and have it work just like it was when you call up over the phone to do it in the old days. So, not that a lot of you probably know that, but that's how we used to do it. All right, so that takes us to programming. So, one of the things about the Commodore 64 is the day it came out, Commodore released also the Programmer's Reference Guide along with it. And that made a huge difference in being able to learn how to program on it. It had every detail about every chip in the computer, all of its registers and how they were mapped in memory. It had details about how to create sound, how to create graphics, how to do sprites, how to work in both basic and assembly language. And probably the most important part of that is the memory map. Here you'll see it. It goes from 000 to FFFF, which is 16 bits. And you can see that when you turn on the Commodore 64 computer, you'll see that only 38K is available. That's because it takes the ROMs with the basic, the character, and the kernel ROM and maps them into RAM memory. So you can't use, well, there are ways you can use it, but at least initially you can't use it that way. Also, all of the I/O, the screen memory, all is used in that RAM. So you have to, if you're not programming in BASIC, if you're in assembly, you have to know where everything is to work with it. You'll notice one funny thing here is kernel is spelled a little funny. If you're familiar with computers, normally kernel is Kernel. This was actually a typo by one of the developers at the time in 1980 when they were doing the VIC-20, which is the predecessor of the Commodore 64, and that just stuck across their line, so it was always called the kernel. The kernel is sort of interesting though, because they created a map of common system routines at the very top of the kernel that are always in a fixed address that point to to where the actual code is. And so you can replace those and replace a lot of the system routines in there, and they can replace them without breaking software. So that was sort of an interesting design for the time. Here's a little more about when you get into the details on the memory maps. You can see things like how you control, when we were talking about sprites, you can see how you can control the X and Y coordinate of each sprite, how you can, look for sprite collisions, how you can do priorities, things like that. And then for programming audio, you can set the frequency to get different notes, you can set the waveforms, just about everything else. And we'll get into that here in a minute. All right, and I should talk about PETSCII. Most of you probably know what ASCII is, or Unicode now, but PETSCII was Commodore's version of ASCII, and it had some really interesting things in it. Besides the normal characters, you could basically control the color of characters that you were about to print out. It had all sorts of little graphic characters, so a lot of games and programs were done entirely with character graphics rather than turning on a graphic mode to do things. And anybody who was programming on the Commodore 64, your first games that you developed were always just using character graphics, so it was sort of fun. All right, so let's take a quick look at Commodore's BASIC. If you haven't seen BASIC before, this is how it looks like. Every line has to start with a line number. The program runs in line number order. So there's a simple hello world up there that prints hello world 10 times. But to do almost anything else, because the basic that came with the Commodore was fairly limited, you would use poke and peek. Poke is to basically stick a value into a place in memory. Peek is to read a value out of a place in memory. And so if I wanted, for example, to turn the background color to black, I would have to poke 53280 with 0. 53280 you'd find out was the background color by looking in the programmer's reference guide. And so you'd be going back and forth between those to do it. Now, interestingly enough, about a year after the Commodore 64 came out, a 16-year-old in the UK named David Simons wrote an extension to BASIC, and it became known as Simons BASIC. Commodore actually released it. It added 114 additional keywords, allowed direct coding of sprites, graphics, and sound, and creative computing at the time stated that Simons BASIC almost makes the Commodore 64 a new computer, probably the one it should have been in the first place, and so that was sort of fun. But really quickly, when you started, if you really got into development, you'd realize that BASIC wasn't going to be powerful enough or fast enough. It's an interpreted language, it's fairly simple, and you wouldn't be able to get it. So you'd very quickly move on to assembly language. Now, assembly language is very close to the real language the computer understands. It's just a simple, readable version of the opcodes that the processor works with. So in the 6502, you've got 56 instructions. With special addressing modes. You've got only 3 registers in there. The accumulator, which is where all the action happens if you want to add or subtract. You can't multiply or divide, by the way, on there unless you do it through adding and subtracting or shifting bits. And then the X and Y registers, which are used for indexing, basically mostly for indexing into memory, but to also keep counters and things like that. And you have a stack pointer, so you can push values onto the stack and pop them off the stack. You have the only 16-bit register is the program counter, which keeps track of what the next instruction that's going to be run is. And then finally, a 7-bit processor status. And this was very important. It had bits for whether, after each operation, these would get set, whether the result was negative, whether it overflowed, whether it carried, whether the result was 0. And those were extremely important to being able to do things afterwards, to do comparisons and to branch to different places depending on the result. And the functional groups of these commands were load and store. Load and store are basically loading from memory into a register. Store is storing from a register back out to memory. Stack operations to push and pop things. Arithmetic, add, subtract. That was your arithmetic at the time. Logical shifts and rotates, which those you could use to do sum multiplication because you could multiply by 2 and other values. And then branches and subroutine flags. If you look at the little chart over there, it's sort of interesting. You can see these are the load accumulator, load X, and load Y from memory. And it has the different addressing modes. It shows you what opcode those actually convert to. And then also tells you how many cycles of the processor that particular instruction takes, and how many bytes it takes to represent that particular instruction and its data. And so you're definitely working very low level on here when you get into it. Now, for the most part, you didn't need to know those details, but you needed to know how each instruction worked. I don't think I'll get into all the addressing modes, but suffice it to say, it had some special ones at 0 page, which goes from 0 to 255. It's only an 8-bit address space. It can work a lot faster. So there's a lot of address modes for working in that first 255 bytes of memory. Had a relative offset where you're doing a branch, if you're within 126 to 129 bytes either way, it could encode the instruction with less bytes and take less time to do it. And then it had some special indexed modes where it could index into a table of data or index into an array of pointers to jump to different locations. All right, before we actually start coding on here, I'll just show you one example program here. And this is just the equivalent of loading, of saying C equals A plus B. So if we have A in, has to be in 2 bytes because we're doing 16-bit adding here. So in address 20, we have the low byte of A, and address 21, we'd have the high byte of A. For number B, we'd have it in 22 and 23, and the result we want to put in 30 and 31. So the way you'd have to do that is, first of all, load the low byte of A into the accumulator, clear the carry bit, because you're going to be adding and seeing if there's a carry after it, and then add that to the low byte of B, and store the result in address 30, the low byte of the result. Now you would basically repeat that for the high byte, but the carry bit may already be set. If it over went 255, it would set the carry bit and automatically add that in. So you'd load the accumulator with the high byte of A, add the high byte of B, and store that in the high byte of C. So A plus, C equals A plus B took a lot of little lines of code there to do that. But it did it very fast, and now we'll show you how it all works. So let's switch to the Commodore here. Any questions so far? I know I go fast by nature, but so there's a lot there. Let's see what happens. All right, there's the Commodore 64, and that's how it would come up. Boots very fast. That's one nice thing about the old computers. Didn't have much boot time. Now I'm going to immediately go into the special software that the Commodore 64 Ultimate provides, and this is their little software, so I can set up a USB drive as a Commodore 64 disk, and mount that disk, which has some programs I'm going to work on. So let's get started here. All right, I'm going to show you a little bit. We'll first of all do a simple basic program. Of course, the old hello world. And if we run that, it says hello world, but that wasn't too exciting. Let's do something a little more interesting with it. Let's say we wanted to clear the screen. Well, one of the fun things about that pet ski stuff that I was talking about is I can actually press Shift Clear Home on here, and I'll put in this weird reverse heart character. Well, that reverse heart character is actually the ASCII code for clearing the screen and going to the home location. So now when we do hello world, it goes to the top of the screen. Now let's say we want to get a little more interesting about this, and before each character, on my keyboard here, I can hit Control and any of the number keys, and it will change the color of the character. So for example, make that white. We will make this one red, cyan, and we'll stop there so it won't take too much time doing it. But now if we run it, you'll see that it did a few different characters. So that was a lot how you'd initially program the computer and have some fun with it. And the most important keyboard combination on the Commodore 64 was run, stop, restore, which would reset everything back to its normal state. Let's load a little sprite program, since we were talking about sprites earlier. And this is how you'd load off the disk drive. The 8 is the first disk drive. Most Commodores only had one drive. It was really hard to hook up 2 disk drives to the Commodore 64. You'd actually have to go into the drive and change some leads on there, and so it wasn't the easiest thing. The 1 tells it to load into the memory where it was originally saved from, which isn't as important for BASIC, but all right. So now, this program, most of this program is the data for the sprite, and I won't get into too much detail, but it's a bunch of bytes that represent pixels that are going to be, you'll see a little Commodore balloon that's going to come up. But the important thing is how we program that. So the video chip starts at 53248, and we're going to do a bunch of things. First of all, at that address plus 21, we can turn on sprite 2 by setting a bit there. At another location, we tell it where to get the data for the sprite. So we actually have to move this data that's here into that memory. So we're basically reading from this data and poking it to 832 plus n. 832 is the 13th memory bank for sprites. I know I'm saying a lot of stuff here that probably doesn't really mean anything, but the key here is to get the idea of how you were programming it. This one's important. V plus 5 is the Y position of the sprite. So we're basically saying put the sprite at line 100 down on the screen. And then what we're going to do is have it go from 0 to 255 along the x-axis by poking V plus 4 with the x value. Do next x, and then we'll go back to 30, which will start the whole process again. So it should go across the screen over and over. Well, let's see what that looks like. So there's the epitome of graphics at the time on the Commodore 64. Now let's say, you'll notice one of the things if you watch it, it doesn't go all the way across the screen there. That's because we have you'll see that we had x going from 0 to 255. Well, let's see what happens if we try to fix that by going to 360, which would take it all the way off screen. So if we run that now, let's see what happens. Oh, we get an illegal quantity error. What does that mean? Well, it means that we tried to poke a value above 255, which is the highest 8-bit value, into that register, and that just won't work. So what we're going to do instead is add a little code here to basically, there's another bit where we can set the high order bit of the X position, and then let it go across from 0 to 60 to get the remaining, or 0 to 80 something, to get the remaining value. So let's go ahead and do that. I'll type that in, and you can watch me type for a few minutes here. Hopefully not too many. 31, we'll go for X equals 0 to 360. Probably the hardest thing for me programming here is forgetting that this does not have You can switch to a lowercase, uppercase mode, but it, by default is always uppercase, so I keep shifting when I shouldn't be. And what we're going to do is do a modulus operator to go from, so that it rotates from 0 to 255 in the low bit, and then it just sets the high bit when we go beyond 255. But this basic does not have a modulus operator, so we're going to have to do it ourselves. So we'll do X.
How do you remember all of this? Like from
Well-
like so long ago.
Some of it came back to me, some of it I have written down here so that I don't forget it.
How did you, like, did you have to, well, you had the manual, right?
Yeah, you have the manual.
So,
Yeah, so
did you look it up on the manual?
Yes.
Or did you, okay.
yeah. Now, some of this I looked up on the internet too these days.
Yeah,
It's just so easy to
did you
find.
look on the internet?
And ironic, you can use AI to write these programs very easily. And
Stop,
I did.
you can
yeah.
use AI
AI
to
will
write
write
this?
Yeah, it'll write really good Commodore 64, both assembly language and basic. So yeah, it's.
That's wild. It also looks like you're in a terminal, which is crazy too.
Yeah, that's what you are all the time, and I'll show you some.
I feel like this is why terminals look like the way they
They
do.
do.
Oh,
This is my
really?
theory.
To like,
This is my theory. It's like it's a nerd nostalgia.
Now,
yeah.
now this has this actually
Oh,
has
all one word.
a scan line filter on it to make it look like an old monitor with scan lines. You can turn that off on here, but for me it truly does give you that feeling of being on a terminal. And you'll see in a few minutes it actually does change how things look as well.
Also, the clicking of those.
Oh, yes.
This just sounds so nice.
Yes.
I was gonna say was the original keyboard that nice?
It's exactly like this, yeah.
Oh,
It's-
okay.
this-
Amazing.
this-
Like,
that's
that,
like a good
that
keyboard.
sounds nice.
It was a good computer.
It'll make like any like hipster, happy.
Let's see. V plus 6. Oops. See there, I did the plus with a shift and then forgot. So 16
Did
with.
anybody else here and actually program in BASIC?
Did a version of Basic.
yeah.
I did like MS BASIC. Back in like
Yeah, that's a.
in the late 90s, early 2000s was probably the first.
Yeah, I used one called Real Basic.
Yeah. All right, so what we've done here is basically changed it so that we set both the low and high bit, and we use a modulus to rotate through the bits. So now what will happen, and you'll notice something else about this. Once it starts, let's see, did I get it? Nope, I must have messed up. There's the other fun part. Let's see. Do a quick check.
Yeah, how do you like test bugs on this?
How I'm doing it right now, just start looking around. Now, when you're working in assembly language, you use a thing called a monitor, which would allow you to look at registers and look at memory addresses, but it's pretty low level even there, because you basically have to know where you were trying to get something from and what the value should have been, and then just hunt for that value.
Although it did tell you when you did.
Yes, some,
Yeah, it was
yes.
like, no, it's not gonna work.
yeah, some errors it will tell you, and I think I did things from 2 different versions of this. Let me just load up, hang on a second, let me do a little. This is how you get a listing of what's on disk, and it actually loads as a basic program, and then okay. So let's see if I had it in script. So, because now I don't want to type it again. If not, we'll just skip it. But let's see if that's the only thing. Oh no, this is one with lots of other ones. All right, well we'll just run that for fun. Okay, so here we have 3 sprites of different sizes, and I'll just show you how that works. They're all using the same data, so let's take a look at that little program just so you can see. The only thing we did differently here is we poked the number 13 to tell it where to get memory from for 3 different sprites, so 2042, 2043, and 2044. And then we're setting the X and Y positions for a bunch of different sprites. Each time it steps, and that's all we do there. All right. Before we get into assembly, I do want to do sound, so I'll skip what I was going to do there.
I have a question.
Yeah, absolutely.
So why did the line numbers kind of skip a bunch of numbers?
Oh, that's by habit. You do 10 as a programmer in BASIC. You would number it in tens, so that you can do exactly what I did: is start putting
Those
numbers
are
in
your
between.
own line numbers.
Yeah.
They're not.
Right. You can number a program any way you want. So I could have said, so if I do a new here, I could say 200, hello, if I can type hello.
So
I do 300, go to 200, and run that, and it'll start printing hello.
So you don't have functions
Yeah.
and you jump to a line number.
Yeah, you go to line numbers. That's all you had was to jump around the code with go to.
Yeah.
Now,
Is it required
So
that
that's-
every line number has to be strictly greater than the previous line?
yes, it actually puts them as a linked list internally, and it reorders them as it goes based on the line number. Now, the original BASIC had no way to renumber lines other than typing. Now, if I go back up here and type this, anytime I retype something and hit enter, it now has redone that line as 100, but also kept the original. So you can do some weird little things. Later BASICs had ways to renumber lines and things like that, and even later BASICs didn't need line numbers. But,
Why would you do like 100, 200, why wouldn't you just do
Makes it easier
101?
to insert.
well,
in-
yeah, see, if I had done 1, print hello, and 2 go to 1,
Yeah.
and then wanted to do something else in between there.
Oh, you're
exact-
stuck.
Yeah,
You have
exactly.
to
Oh, okay.
renumber your whole program.
Yeah.
That's crazy,
Yeah.
so would you
Been
jump
there.
100, like in the hundreds
Oh, yeah.
in order to
Yeah.
get back to?
Yeah, often what you do is your subroutines would be at numbers like 100 and 200 and 300 so that you could jump to there and then jump back to your code. You could, there were ways to do to call a subroutine and return, but yeah, you still had to have your line number, so you put them way out there so you'd have room to write the rest of your code, yeah.
Blowing my mind.
It was a weird world for sure.
Was there a limit on how high the line numbers could go?
That's a good, I think there is, and I can't remember if it's 16, I think it's higher than 16-bit, so I can't quite remember, because it's just interpreted at. I don't know for sure, actually, but I think there is, and I can't remember what it is. Well, let's try
How do you
70,000.
save your,
Oh, okay,
your
I'll show
code?
you that. Okay, I will show you that. Hang on. So you have to remember to do that. Whoops, well, I did syntax here. Oh, I think that is too high of a line number, actually. Let's see.
16-bit is like, what,
No,
65?
oh yeah, it's 60, I don't know, and I don't know, let's see, 535 would be, no, it doesn't even allow that, so 50, I don't know if it, allows 50,000. So I'll have to find out what that is. Okay, to save your program, you would, let's write another quick program here. I would do save test 1, 8 to save it to the disk drive.
And so then how do you recall it to get back to
Yeah,
it?
then you would do load test 1.
So you would have to remember what you saved it?
Well, no,
You can't just pull it up in a list?
you can, and that's where you do this load $8. This load $, will give you a listing of what's on the disk. And so now if I do, whoops, list, liar, I can see that there's test 1, the one I saved. You have to know what it was. And
But you wouldn't know that, like, what date you saved that?
no,
Okay.
you know nothing
You
like
just
that.
see it.
Yeah, you just see it there. No, it was pretty, you had to know what you were doing. All right, so let's, oh dear, I got myself in, let's do one stuff. Oh, now it thinks I'm on tape. I may have to, let's see. Let's reset here. Yep. All right. Every once in a while I get myself in the mode here. Oh. Okay, there's that. Let's see. Let's do it. All right, take a second here. And it's not much different than how it was programmed. You would often get to a state where you had to reboot, so you would save often, that's for sure. All right, so let's load a little sound program here. Whoops. Oh, I gotta.
I like the little noise it makes too.
Yes, that is, they have reproduced the noise of the original disk drive, which is sort of amazing. And that was a joyous little thing that it did for me. All right, so that, all right. Back up here. Let's go. Okay, and let's list. All right, so here's a little sound program. And so the first thing it does in this line is just clear out every register in the sound chip so that it's starting from a known place. And then what it's going to do, then this just is a little loop to waste some time. And then here it's setting things for the sound chip. So first thing it's setting is the overall volume that's going to come out, which is 15 is the highest volume. Here it's setting what's called the attack, decay, and sustain release values, which are the shape of the waveform it's going to do. Then the reading here is just going to read these values, which are going to be the frequencies that are going to be played out. So it's going to keep reading data until it's negative, until it gets a -1 value, which are the last values on there. And then it's going to poke the A and B values, which are the high and low frequency values for a particular note, into the proper registers. Then this one is setting the waveform, or the waveform type, which I believe this one, I think is a triangle waveform, or sawtooth waveform. And then a little delay, turn off the note, a little delay, and go back to the beginning. So what does this do? There's the excitement of it all. Okay, now, if we wanted to change the waveform, let me get to my notes here because I do need to know the values of this. We'll go from 33 to 32 instead of 17 to 16. And we're going to hit the turn, otherwise it's not going to save my changes, by the way. So that's another thing. And now we get a little different sound out of it. Super exciting. All right, and let's change a couple more things just so you can get a feel for it. So if we change the attack, decay, sustain, release things, let's see, we'll change that to 3. A little different result. That's supposed to be a banjo, by the way, if you look at their guide. So you had to use your imagination even in the sound in those days. So.
Would this just blow people's minds?
It would. Now, what would blow people's minds is what they did with it, which I'll show you a little later, because you can get really advanced with the sound with it, and I will show you that. For now, let's go ahead and get into assembly language, because I think that's, for me, the more interesting thing. So we're going to load an assembler called Turbo Macro Pro, which ironically I knew nothing about at the time when I was programming. It was a German program, but became the most popular assembler. I used Commodore's assembler, which was fine, but not quite as good as this one. And it'll take a moment to load here. So what we'll do is start with the Hello World program, and we're going to do it 2 different ways. So let's see what that does. And then we'll load up the same sprite program we did earlier, but in assembly, just so you can see the difference in speed. And a few other little details. So, okay. I guess I'm going to take up the whole time tonight. Hope that's all right. Take up the whole time just loading the assembler, by the way.
That space around it, is that just how the monitor was? And so it's just...
Yeah, that's the border was part of it. You control the color of the border.
Oh, you did?
Yeah. And there are some demos where they've been able to put stuff in the border that normally you're not supposed to be able to do, but yeah.
Like they hacked it or something?
Yeah, they hacked it, yeah.
So imagine like this, there's like CRTs,
Uh-huh.
and so you have to have kind of some bleed off,
Yeah.
Sure.
and then the corners are like rounded and
Yeah.
stuff, so
So
like,
you have to have some kind
You
of
can't
really
padding
go
in
all the
order.
way.
Exactly.
Yeah.
It was basically the safe zone that you have in video
Yeah.
today. It's the same as that. All right, so now to start the assembler, we actually it's loaded to a different place in memory than BASIC because it doesn't want to be in that same place. So you have to know where it's loaded.
islands and stuff.
So we're going to do this, and we're immediately in the macro assembler.
And the swipe bottom.
All right, so the first thing we have to know, this is another thing you'd find from the programming guide, is that there's a built-in kernel routine to output a character, and that's at FFD2. So we're going to do that. And what we're going to do, and we want to put it on a message, so let's go ahead and put in the message first. Can you see that? Can everybody see that okay?
Yeah.
I know it's a little faded, but I can't change the color very easily. So we'll do hello, whoops. I wish I could type. And because we could do a null text, but I want to also do a line feed to it, so I'm going to add 2 bytes to the end here, which are a line feed, our carriage return line feed, and then our null byte at the end. And that's going to be important, otherwise it'll just start printing through memory and do some really weird stuff. All right, so how do we print this out there? We have this message. These are bytes in memory somewhere, and luckily the macro assembler does make it much easier than doing it directly in memory. So what we're going to do here is we're going to have to start first of all, we have to tell it where we're going to put this program in memory, and we are going to put it at 0810. There's a reason for that, is just a little past the beginning of where a basic program would be. And what would normally happen is people would write an assembly language program with a few bytes of code at the beginning that were actually a little bit of basic programming to jump to the beginning of the assembly language so that you could load the program and type run. Because right now, the way it is, I can't do that. You'll see that here in a minute. I have to actually jump specifically to that location. All right, so how are we going to print this out? Let's do a bit of line here. So the start of our program, which is 0. So we're going to use the X register as an index. And we're going to start a loop here. We're going to load into the accumulator from that message indexed by X. So message is the start of that memory where that hello world is, and X will be our index to the first character right now since we have 00 in there. Then what we're going to do is, let's see, oh yeah. Now, we're going to do this thing called break if equal to done. And what that means is it's break if equal to 0. I told you about that status register, is after we load something into the accumulator, if we load 0 into the accumulator, it's going to set the 0 register. So we don't have to do a compare or anything. We can just immediately say branch of 0 is what that really means to done. All right, and then we will, if we're not done, we jump to subroutine of that character out routine. And basically, that character out routine will output the print character and then call RTS, which is return to where it left off. So you could do subroutines in assembly language. And all right, so then we'll increment the X register to get the next character. And we will, we're just going to use break if not equal as just a fail safe because our message is less than 255 characters, so it doesn't really matter. We'll do that, and then we move our done register. And this one, whoops, jump start. What this last one does is tells it to jump back to itself over and over, so it's going to go into a type loop when it's done. All right, so we're done with our first program. How do we run it? Back arrow 3, you have to know that one. And it has now done the 2 passes of assembling, tells us that I have no errors, and we can hit S to start the program. What does it do? It prints hello world right there. Now what do we do? Nothing. Well, we don't know what to do because it's stuck, we can't print anything. If we hit run stop restore, it'll take us back to basic. And if we want to run that program again, we can jump to where we put it in memory. That 0810 is 2064 in decimal, and it'll print hello world again. Now, interesting, you'll notice it printed uppercase because we're in uppercase mode. That's one of the oddities here. If we want to get back to the assembler, we go back to here, and we'll make some changes to it.
But I'm confused, like, so you have basic, which is what you just showed, the blue.
Yep.
What is this?
This is assembly language. Assembly language is just, basically gets compiled down to the machine language of the computer. And now, I say compiled, it really gets assembled down to the machine language. So these are truly individual instructions of the 6502 processor. So load X with 00 is a single instruction in the 6502 processor to load memory, to load that register with that number. And so it's the really, other than typing in the actual hex codes of these things, it's the lowest level of programming you can do on a computer.
Okay.
Yeah, so you are really directly, anytime you're writing a program in Swift or anything else, sooner or later, it's getting down to machine language, effectively assembly language.
Okay.
And so everything always gets down to just a lot more of it than what I'm writing here.
Have you talked yet about the operating system? Like, what is the operating system?
The operating system was what you saw there, the basic interpreter. That is the operating system. And a number of the routines like the load, to be able to load from disk and save to disk. That's it. That is the operating system. So everything.
When we talk about like the binary code, when you compile the binary, if you look at the actual binary, the zeros and ones, and you split them up, the first, like say you look at 4 bytes,
Yep.
maybe for on a 32-bit processor. The first byte is going to be some number, and that number is going to be the code for load X,
Right.
or load A.
Right.
Okay.
And then the other 3 bytes are whatever goes with that command. So the rest of this would be like all zeros. So it'd be load X is the first byte, all the rest are zeros, meaning put the value of 0 into that X thing. And then there's another code that means, B and E, so break if not equal, and another code that means jump, and then the rest of it is where you jump to. So that's like what raw binary is. And then there are programs called disassemblers that take the raw binary and turn them back into these more readable instructions
Yeah, that humans can read.
that humans can kind of read.
Yeah.
And then there are patterns that you can apply to the raw instructions to actually say, oh, this is a for loop, because I know how for loops get turned into assembly code. Therefore, if I see that assembly code, I can reverse it back into a for loop, and then you actually end up with pseudocode that you can read.
All right, so let's make a few changes to this. This is one way of outputting. The one thing I didn't do here was clear the screen like I had done in my basic version. So to clear the screen, what we're going to do is load the accumulator with the value, well, let's just use the decimal value of 147, which happens to be the ASCII code to clear screen and go to home. And we'll also character it out at the beginning of that before we do this. Now if we assemble that and we start, this time it cleared the screen before the big accelerate. So now let's get a little more interesting with that. Get back to the assembler, and we're going to change the way we output. We're going to write directly, because in the Commodore 64, rather than just outputting characters, you can place characters anywhere on the grid on the screen and change the color of any character on the grid on the screen. You just have to know where those addresses are. So those addresses, the screen address starts at, let's see, where does the screen at? 04, $0400. The color starts at $D800. Okay, and let's see. Oh yeah, let's also set the color of the border and the background just to make it more interesting. So we're going to load the accumulator with 4 and store that into address D021. That is the address to set the background color of the screen. And we will load color 1 into D020, which is the border color, oddly enough. We did that backwards. Okay. So let's get a little more interesting here. So let's see if I can remember how to do this. This all seemed easy when I'm doing it on my own. All right. So what we're going to do is have 2 indexes this time because we want to store both a color and a character. So we're going to load the Y register, number 1. Whoops, what did I just do? Load the X register with 00. I believe it is, oh yeah, okay. Sorry. Let's try okay, all that's the same so far. Let's go do okay. All right. So next thing we're going to do is break if equal to done. But this time what we're going to do is take the we're going to store the character that we loaded into the accumulator to screen memory on the same index. And then we're going to also store, oh yeah, we're going to load it. Okay, here's we're going to do a different instruction. We're going to transfer the Y register to the A register. So the Y register is going to be our color that we're going to be storing. So we're going to basically take it now, transfer it to the A, because you have to do everything from the A register. We're going to store that to color X. All right, and then we will compare if we've gotten a 16 on the color, and if we look at the next character, which I'll have to put in here in a minute, we'll reset Y back to 1. So what we're doing here is basically saying that Y can go from 1 to 16 and then has to reset. And the next character, oops, X. All right, so what we're saying here, and I sort of went through that a little oddly, is we're saying we're going to load the color that we want to put on the screen into Y. X is our index into both the message and the screen and color memory. So we're going to load the character of the message into the accumulator. We're going to store that to the screen. We're going to transfer the Y register, which is our color, into the accumulator, store that to the color portion of the screen memory, and then check and make sure we haven't overrun the color. So now if we run that, oops, no, it should have been a different color on each character, so let's see what I did wrong. You can see at least we got the colors right on the background. All right, so let's quickly take a look at what I did here. Oh, I forgot to increment Y somewhere. That would have been helpful after we stored the color. Let's increment the Y register, so it wasn't changing color because we didn't increment the Y register. So now if we hit And you can see it did it in different colors. So, not the best colors, by the way, but you get basically the idea. All right, last thing we'll do here, before I show just two little demos on it that are much more impressive of what the computer can do. Let's load up let's first of all do CS, load, base.0. Okay, this is one I wrote a little earlier, so you don't have to watch me type all day. Okay, what this is the sprite program we did earlier in BASIC, to have a sprite go across the screen. And so here we're doing the same thing. We have the video chip starting a certain register. We're clearing the screen. We are, in this part, loading the data that I've got down here for that sprite, it's the same data we had for the BASIC program, into the right memory locations. And then we are basically turning on that sprite. In this case, I did the binary number instead of the hex number just for fun. And then basically, okay, at this first point, we're just going to put it on screen. There's a reason why I did that. And we're going to just put it at 100 pixels and have it sit there. So let's see if that works. And there's our sprite at 100. All right, now let's have it move. Okay. So we will delete that line, and we will delete the forward. Okay, so now what we're going to do is let it go through and basically increment through the X position 0 to 255, basically. And let's see, oh yeah, I'll keep it, okay. Yeah. And we don't even need to do a comparison. When it increments X, what it's going to do is increment from 0 to 255, and then automatically when it hits 255, it's going to go back to 0 because it's only 8-bit registers. So let's see what happens here. But this will be interesting. It's not quite what we expected.
What?
Yeah. So why did it do that? Well, here's the interesting thing, is that we are basically, because the machine language is so much faster than BASIC, we're beating this scan line across the screen. So in your old monitors, it would run a scan line going across the monitor 60 times a second, or 30 times a second, depending on the type of monitor. And what we're doing is changing this value before it can get to the next scan line, so we're seeing it smeared across the screen like that. So let's do two different ways to fix that. Okay. So the first one, let's just put in a little delay here for fun, and delay before we move. Okay.
You're just trying to move it across the screen?
That's all we were trying to do, is move it across the screen. That's what it's sort of doing there, but yeah. Let's see.
Did they have designers on these?
There were a lot less designers at the time. Designers became there.
No.
Not particularly often.
There were.
I mean, there were game designers, and there were designers, they were less prominent in those days, I think, than they are now, actually. So I think it became more important. The more capabilities the computer has, the more design becomes important, to the software, I do think. So.
What happened to this company?
Commodore?
Yeah.
They finally, at some point, went out of business, and that's when some of the other people bought all their IP, and, but it was
Why
like...
did they go out of business?
The Commodore Amiga did well at first, but didn't keep up with like the Macintosh and other computers.
Have you heard of Commodore before tonight?
No.
No,
That's why.
Yeah. But they were one of the biggest computer companies in the 70s and 80s. Faded in the 90s. By the end of the 90s, they were pretty much gone. Though Commodore's, there's still Commodore computers around. There's still people programming them around the world. But obviously, it's not a very big, community compared to
niche community.
It's a niche community for sure. Yeah. Okay. So right here, what we'll do is put in a little delay. So what we'll do is say load accumulator with FF, which is 255, which is the highest number the register can support. We will decrement it. Let's see, delay here. Decrement Y, that's just the name of the label we're going to have here. So we're going to decrement the Y register and break if not equal to delay. So what we're saying here, start at 255, decrement the Y register. When it, as long as it's not 0, keep going back and doing it over. Once it gets to 0, it'll jump back up and move to the next position. So we're basically putting a loop of 255 instructions to sort of delay it, and we'll see what happens. Well, that's better, but boy, it's still sort of ghosty, and so we haven't done it the right way, so let's do it the right way now. And this is where you'll see that we really have control over all the hardware here. So we will do, let's see, okay, get rid of that. All right. So now instead of just doing a loop in here, what we're going to use is another location. I'm going to say wait for bottom, and that's going to say load the accumulator with D012. What is D012? it is the current scan line that is being drawn. And so the VIC chip, as it's zipping down the screen, is updating this register with what the current scan line is. And so what we're going to do then is compare that. We will do compare FA, which happens to be line 250. So about line 250, it'll be near the bottom. Whoops, and I obviously typed something. What did I do wrong? Oh, label missing.
So there's no mouse in there,
Oh.
right? Huh? Did I have a mouse?
No, I did not have a mouse, that's for sure.
What do you know that?
You're starting to see why, like, the creation of the Mac was so revolutionary. You could graphical user interface.
Yeah.
Yes.
You could move around and click on things.
Is this why Apple just went
Apple
across
was
the
the
competition?
first to have phones.
I knew that because he like took a class or something
Yeah.
in college and it was
Yeah.
like typeface or something like that.
Yeah, and so we
Yeah.
just thought the importance of that. And so Apple was one of the first to actually like put emphasis on
design
design
and-
and graphic
Absolutely.
interface.
Yep. So now what we're going to do is wait till the scan line gets to the bottom and only increment the X register every time we get to the bottom. So if we do it now we get a much smoother
Oh, nice.
spread right across. All right. So that sort of gives you an idea of just how much detail you have in controlling things, but also how much you have to control things to get it done. So let's really quickly just show you a couple of good demos here. I'm going to show you one that I remember very fondly. This was a demo of a game that was supposed to come out that never came out. A guy by the name of Jim Sachs later came out with a game called Defender of the Crown that was well known at the time. And this was a cool little demo that he did. And it'll take a moment to load. And then I'll show you two other short demos just so you can see what people both in the past have been doing and what they're doing today. Because one of the demos I'll show you was written in last year, basically. And there are hundreds of demos coming out every year on the Commodore 64. It died off in the 2015 to 2018, started coming back up, and during COVID, I think people got back into the Commodore 64 and it just spiked. You know, there's new games coming out, there's new demos.
Really?
It's become almost a retro world to sort of go back to something simpler and more fun, you know.
Are you running a disc? What do you run, like?
Yeah, so right now I am loading it. I mounted a disk image from USB, and it's now loading a program.
On a USB?
Yeah.
You can run it on that?
Yes. Now normally you'd have to have disk. That's one of the nice things that the Commodore 64 Ultimate has, is it can mount anything off a USB drive that is in the
But it's still making
disk format.
It's
Yeah.
still making floppy noises.
Oh yeah, they just did that for fun.
Yeah.
Yeah.
Oh wait, so is this like a newer edition?
Yes.
Yeah, this came
Oh,
out.
I thought you were just
barely
using
came out.
ones
No.
that you just had.
This looks
The box
identical
isn't
to it.
yellowed enough.
I was so confused. I was like,
Sorry.
wait, what is going
Yeah,
on
so
here?
this, like I said, this is a faithful recreation of the original Commodore 64, but it actually has an AMD FPGA chip in it where they, oh here, we'll let this go first.
Oh my god.
Reminds me of the reggae game so much.
Is that pixel art?
I was wondering earlier how it was, like, that we have the correct cable to do this.
Yeah, that's it. I was like,
Oh.
they were thinking of the future. Like they should have.
Yeah, because at the time all it would have was a composite out, which you would normally hook up to your TV using an RF modulator.
Yeah.
It would hook up to the little antenna, leads, and you get this horrible picture on there. So yes, this is why I like this version of it, is that it has a lot of the niceties of current, computers, but also allows me to program the way I did back when
Yeah, that's so
I was 15 or
cool.
18 years old, so that's fun. There's one more little part to this demo. I know it looks weird, but that's because it's still loading stuff.
Who made this then?
This,
newer version.
so it was original, some of the original hardware engineers on the Commodore who got together, along with a bunch of new people who had money and investment, decided this would be an interesting idea. They bought up all the Commodore IP from people who owned it, and
Oh, wow.
work together to come out with this. So there's been a couple of other attempts to do that in the past, but nobody's done it as well as these guys have.
It's the 8-bit guy, isn't it?
Yeah, no, he just shows it. He's not one of them. I don't think
I thought he was like the CEO or something. He's
I
the.
don't think so. There's somebody else, but maybe not. I may be wrong. Now, for me, back in 1983 when this demo came out, this was just unbelievable how great these graphics
Yeah,
were.
sure.
You know?
I mean, I'm impressed just looking at it.
Yeah, because really nobody thought the Commodore 64 could do anything that impressive, you know, with its 16 colors and 320 by 200 pixel graphics. So that was the whole demo. Okay.
Wait, so it's not a game?
It was going to be a game and he never finished it. So all he put out was the demo.
Oh,
You look at that water.
I think
Water's cool.
you could play the demo a little bit, but not very much.
How different does the UI on this look compared to like an old school monitor?
Oh, probably.
It's,
The colors are very different. But
it's actually, I mean, they've reproduced, with the scanline reproduction, it looks very similar to how, it feels to me exactly like it felt back then. Yeah. I mean, other than it probably is a little cleaner because, you know, the signal's digital rather than analog, but, so let's see.
So if we wanted to buy one of these Ultimates, how much would it cost?
It's $300.
They started making them again.
Yeah. Now you can get the gold edition for like $600, or the clear edition I think is like $350. So you can see the insides, but.
Can I see the box?
Yeah, of course, yeah, come see the box. You can look, they've also done a really nice job of redoing the user guide, which gets you into the initial programming of the Commodore 64. Has some really fun stuff. Let's see, I was going to do, let's see.
What if I just get into this? Just kidding.
Wait, the pictures.
What's it called? I can't find. Okay. Let's do this original demo. This was called, this was one of the early demos that somebody did to show off the their idea of graphics and sound. This is one from 1985, so it's a little more basic. Then I'll show you one from last year, if I can find it. Yes, waiting for things to load was your life back then. But you'd be in the meantime reading the program's guide in between that, reading magazines, so yeah, it all worked nicely. All right, here it goes. I'll take it. And almost all the demos started this way with all the people who worked on it, so you'll have about a minute of that before it starts getting fun. Now this one was interesting because it was done entirely with sprites. There are other demos where they've entirely done everything with the ASCII, PETSCII characters and no graphics, but are still quite impressive. Rob Hubbard was well known at the time for his music on the Commodore 64.
Dude, this is sweet. That's cool.
This is a fun demo. I'll show you one more demo. I won't let it go through all of this. You'll be here for 10, 15 minutes.
How did those things go in a circle if all you could do was add and subtract?
Math is all addition and subtraction. You can do any kind of multiplication with addition and subtraction. But now keep in mind, often multiplication would be done by shifting bits rather than addition. Because if you shift bits left, it's like a multiply by 2. So you can do some weird stuff, and that's what was fun about these demos, is people finding ways to do things that. There's one demo here from recently where somebody compressed 2,200 frames of video to run on the Commodore 64. They're all black and white, but they compressed them so much that they fit it in like 100K of memory, you know. So people are just always doing weird stuff like that. Let's see if I can. that again? I can't remember which one. Oh, let me look at my notes.
I like this little mascot that they have.
What's that?
Integer.
Oh, yes. He's cute. What was that?
But I don't remember what it is.
Oh, yeah. I mean, this did have floating points, so you could do floating points. So that was, okay, oh yeah, we are the anomaly. All right, let's do we are the anomaly. That's one of the more recent ones. I think that was done. This one actually has 2 sides to this, but we'll just run a little bit of it just so you can see it. And then I'll finish up here. I'll have 10 minutes to sit and chat. And one of the fun things they did with this new Commodore 64. So you can see they get pretty good music out of those 3 voices.
That's crazy. This is true art, right here.
People put a lot of time and effort into these things. It's all written in that assembly language.
How many hours would it take to write something like this? This is crazy.
So this is an entire assembly game.
Yeah, this is just a demo, not even a game, just a
So
demo.
it took them, wow.
They're just like making art, basically.
Now, most of them probably have pre-built macros that, do portions of this that they just keep reusing, just like you would in any kind of code. But even most of them are developed. So there are websites with literally tens of thousands of these demos and SID music that people have done with Commodore 64 music. This Commodore 64 ultimately, one of the fun things that came with it was this pretend cassette that's actually a USB stick that had all the demo software on it.
Is this a new demo that somebody's made?
Yeah,
or
this
is
was
this
done last year.
Oh, okay.
Yeah.
I didn't realize it's been out that long.
Well, they probably did it on early, there's been other remakes of
Yeah,
Commodore 64. And so this is, because it's just pure Commodore
When did
64.
this new one?
This came out in 25 last year.
Yeah, okay, that's still a little earlier.
Yeah.
I didn't realize it happened already.
Yeah.
People talking about it.
Do you think this person has the Starlight edition? Because I feel like it goes with the vibe.
Yeah, that's something like that.
That one's on sale right now.
Really? Really? How much?
In fact, the Founders is on sale too for like, I don't know, I closed the thing.
How much is it?
All right, so that's all I had.
That's cool. You can connect this to Wi-Fi?